This is Michael Malak. This is a reprise of a presentation that I gave on November 5th, 2014 to the Data Science Meetup in Denver, actually in Broomfield at level 3. Re-recorded here as a screencast due to poor audio in the live capture. You can see the other versions of this presentation at the Data Science Association, datascienceassn.org, under Events. This is about Spark, Gothas and Anti-Patterns. I do assume some familiarity with Spark. If you need some more background, you can see my presentation from April 2013 at technicaltidbit.com and many other sources as well. But I will give a one-slide overview of what Spark is. Spark stores its data in RDDs, resilient distributed data sets. So whereas Hadoop distributes its data amongst the hard drives in a cluster of commodity nodes, commodity hardware, Spark stores its data in the RAM memories of those same machines in a cluster. Spark has different layers of ownership, so to speak. It is open source, mostly. It started out as a project at MLLib at UC Berkeley, and then in 2013 it became an Apache project, and in late 2013 the guys from MLLib formed a startup called Databricks. Databricks does have a couple of proprietary pieces that I don't believe are released yet. The notebook in the cloud, and I believe also a management piece. Everything else is open source, but there are different ownerships, so to speak. I mean, this caught some of the Spark community by surprise this past spring of 2014, when the 1.0 release came out, and the SQL part, which was formerly Shark, was switched out just before the 1.0 release and became a new project, SparkSQL, completely different. And a lot of people in the Spark community were surprised by that. And then the MLLib people reminded us that Shark was never an Apache project. It was only an MLLib project. So from their perspective, the Apache project was gaining a SQL component. So it's good to be aware of who the maintainers are if you want or are expecting continued support. So just to do a little meta here of this presentation. If you want to do your own presentation like this on any subject, the Jira is a good place to dig through. I mean, when people start becoming familiar with a framework or library, they pretty much know automatically to subscribe to the mailing list. But I don't think everybody digs through Jira as often as would be beneficial to them. Daily is not too frequent to find out what problems people are really experiencing with a library or framework or a system. So back to the presentation. We're first going to focus on the Spark core and some of the anti-patterns and gotchas there. The first anti-pattern is to ignore partitioning at your own peril. So here we're doing a group by key. We probably have a SQL background, so we like group bys. But behind the scenes, there's a repartitioning going on that we might not be aware of. Group by, every time you execute it, repartitions the data according to the key you give it. So here we're trying to do a group by the first letter of each word here. And since our words happen to begin only with A's and B's, our data ends up on only 2 of the 4 machines, and so any future operations, 2 of our machines, half our cluster, is going to lie fallow and not participate in the computation. Now there are various ways to remedy this. One way would be to choose a different key. So we could do a group by based on the first 2 characters instead of the first character. This may require some algorithm adjustments later on. There are various other ways to solve this problem. You could do a reduce by key instead of a group by key, and we have a slide on that later on and how that interacts with the shuffle. But our next anti-pattern is ignore garbage collection. So here's a chart of how long it takes to do a garbage collection for various sizes of memory. This goes up to 100 gigs, and for that it takes 300 seconds or 5 minutes. But actually, you can get servers now with a terabyte or even 6 terabytes of RAM. So a terabyte, this scales linearly, so that would be 50 minutes. 6 terabytes would be 5 hours spent in garbage collection. Depending on how you have your garbage collection setting set, it could be stop the world for 3 hours. So there are various solutions. Solution 1 is to use Tachyon. So Tachyon is a layer that sits underneath Spark. Now when Spark runs out of memory, or if you tell it to, it can spill some of its data that it's storing in RAM onto a file. That's typically, of course, that's HDFS. Tachyon is a file system itself, except it's a RAM-based file system. So you can spill memory out of Spark into Tachyon. Now, even though I think the top layer of Tachyon is written in Java, it's fundamentally using the Linux kernel RAM file system, which is written in C. So this is the idea here is to take data off the JVM heap and put it on to the Linux memory, where it's much more easily managed and there's no garbage collection. Another solution is to break up a node into multiple workers. So you have a physical node, and you can have multiple Spark workers on that node. Now there's a study I stole a slide from. This chart might not be easy to interpret right away, but that top line there shows our best performance, and according to the legend, that's when we have 3 workers per node. Now, I don't imagine that the factors influencing this are really the GC RAM issue that I'm bringing up. There are many factors that determine the optimum number of workers per node, and I did not copy the conditions for which that is, but the point is that there is an optimal number of workers per node, and usually that has to be empirically determined. And one of the benefits of having multiple workers per node is that each JVM is smaller. So if you have a GC that takes a long time, it's not going to stop everything. There would be other workers that can proceed. Another advantage of having multiple workers per node is just generally being able to overlap computations on the one node. Alright, our first gotcha, sharing RDDs. It's sort of a natural thing to want to do, right? To think of Spark as a data store in RAM that you want to access. Maybe have multiple applications access the same data in RAM. Well, it's generally not possible, unfortunately. That's because an RDD is tied to a particular Spark context. So, one solution, again, is to use Tachyon or Succinct. Succinct is a new layer that can sit on Tachyon that provides a key value store. And then, since Tachyon is basically a file system, you could have multiple Spark contexts access the same files. The other solution, also not ideal, is to have one continuously running daemon that maintains hold of that Spark context and maintains hold of that RDD, and receives requests from other processes or applications to use that RDD. Now this is really far from ideal because that means you'd probably end up having to do some sort of REST interface. You would lose direct access to the Spark API and so forth. Another gotcha is, if you're putting Spark into production, into a real production system, you're going to eventually want to be able to add nodes on the fly to your cluster. I haven't actually tried to do this, but from my reading Jira, it looks like, and documentation as well, it looks like it could be done in Yarn, but probably not Mesos at this time. In the Yarn documentation, it looks like you could just issue this command here to reread the Yarn configuration. But based on these Mesos Jira tickets, it looks like you have to restart Mesos, especially the slaves, in order to have it recognize any reconfiguration. Alright, another anti-pattern is believing what I told you at the beginning of this presentation, which is that Spark is an in-memory platform. In reality, anytime that you need to shuffle data, which is always, it's done on disk. Shuffles are always done on disk, and then the data is reloaded into memory. Life gets a little better in Spark 1.2. I think Spark 1.2 is due to come out in December 2014. I haven't checked the latest on that. But there is one improvement in Spark 1.2, which is that the reduce operations get mapped to the node that happens to have the largest shuffle file. So it reduces the amount of data movement within your cluster and on your network. This is the slide I promised. This example was stolen wholesale out of this excellent presentation by Aaron Davidson at Spark Summit in July 2014. In that presentation, he takes this original here at the bottom of the slide, a seemingly direct coding of a simple problem, which is to count how many first names, human first names, begin with the letter A, how many begin with the letter B, and so forth. So it does a group by key and counts the unique numbers within each group and reports the results. And surprisingly, during this presentation, he breaks this down step by step and improves the performance. It's kind of a surprise to such a straightforward solution. But one of the many things, one of the many steps that he took, was to replace the group by key with a reduce by key. And you remember that the group by key causes a repartitioning and a shuffling. But by using a reduce by key, we count the number of names that begin with the letter A, say, on each node, physical node in our cluster separately. And then we send those intermediate results to the driver node, and we just add up those intermediate sums for each letter. So there's a great reduction in data movement and shuffling if you can use a reduce by key instead of a group by key. Anti-pattern using map instead of map partitions. So here's another example that I stole wholesale. This came from Patrick Wendell in Spark Summit 2013, and he's using Python here, so you'll just have to bear with the Python. I like Python and IPython Notebook. I just really haven't used it for Spark, but you can read it here. So at the top here, we're doing an expensive operation. We're creating a cursor. And because this is inside a map, we're creating a database cursor once for every element in our set, in our RDD. So if we have 1 million elements in our RDD, we're creating 1 million cursors. So map partitions can help in this respect. a partition gets mapped to a worker, and a worker runs on a single core. So what we do is for each worker, because we're using mapPartitions, for each worker we create a cursor, and then we run serially with a good old-fashioned for loop through our data using that cursor. And remember, this is a single core, so we're not losing any opportunity for parallelism here. And then we finally close that cursor. So mapPartitions allows us to do these expensive operations once per worker. Another anti-pattern is going down the cryo rabbit hole. Life has improved substantially in the 1.0 and 1.1 releases. But there are still issues with cryo. If you're trying to use cryo with Avro on anything moderately complex that involves arrays or structures, there are still issues. Now, just to back up here, what am I talking about cryo? So in Spark, everything has to be serializable. You're instantiating objects, you're sending them out over the wire to worker nodes. Everything has to be serializable. So your three options for serialization are to use the default Java serialization called serializable, or you could use the Java externalizable, which is just an interface, and it's up to you to implement custom serialization and compression, or more likely just forward those calls to a standard compression library. Or three, you can use cryo, and Spark has first class knowledge of cryo. So there's a 10x performance difference between default Java serializable and cryo. So people are naturally inclined, when they want to improve performance, to look to cryo, but it can just lead to a lot of trouble because there are still some issues. So one is this Avro, and another is with Snappy. Like I said, I haven't actually used cryo since 0.9, so it may be suitable for your purposes by this point, but just be warned, there may be issues, and if you can tolerate the performance with Java serializable, it may be worth doing at least a little while longer, at least until 1.2 comes out, maybe the version after that. Another anti-pattern, mixing accumulators with lazy operations. So accumulators are naturally side-effecting, they're imperative. Lazy operations are non-imperative. And so the output of this little bit of code here, again, one that I stole off the web. There's a map here, and we're trying to invoke this accumulator, and so map is lazy, and so the output of this is just 0, 0. So the naive, straightforward solution would be to replace that map with a for each, but that is completely serial. If our RDD has 1,000,000 elements, the for each will execute 1,000,000 iterations all on the driver and not use our cluster at all. So the compromise is to use mapPartitions and for each in combination. So mapPartitions gets us to the level of parallelization where we're out on the cluster, and then within each worker on each node, then we can do our serial operations that increment our accumulator one by one. That's it for Spark. I'm next going to talk about Spark streaming, which is probably the part of Spark that I'm most familiar with. The first anti-pattern is to ignore closure. Well, first of all, what do I mean by closure? And if there are functional purists out there, I'm sure they're going to correct my terminology here, but the whole idea behind functional programming is you're passing around bits of code, functions. So here we have a function that we're declaring called multiplier, and presumably we're going to be passing this function around in the future. And if we want to do that, it's going to need to know about factor. which is external to the function. So when we pass multiplier around, we really need to bundle up factor along with multiplier. And functional programming systems do that. Scala does do this. Scala has closure. But Scala does not have closure with serialization. Scala out of the box cannot create this closure and ship it out over the wire. Now there is a library out there called Spores. It was going to be included in Scala 2.11, which just came out. But besides, Spark was written in the Scala 2.09 days, or 2.9 days. So they ended up writing their own. So the bottom line here is that Spark has serializable closure, custom written by the MLLib people, even though Scala does not. So it can get kind of confusing if you don't realize that this special closure is going on behind the scenes. So looking at this code here, so the issue here is this variable JSON parser. Now, first of all, right off the bat, we need JSON parser to be serializable. Irrespective of closure, everything in Spark has to be serializable. So assuming it's serializable, there is likely another issue going on in here. So we're trying to pass this parser into a map, and so the parser is instantiated on the driver. We're calling map. Spark is going to serialize our parser, send one copy of this parser to each node. This parser had better be stateless. Now it probably isn't. This is probably not going to work. The solution then would be to put the JSON parser inside the map, or more likely use mapPartitions, as we've been discussing. But the real issue here, the real gotcha I wanted to bring up, is if you wanted to declare your JSON parser, let's assume the JSON parser is both, for the sake of argument, it's both serializable and stateless, for whatever reason. If we wanted to declare JSON parser outside of our main, or even worse, outside of our object, we're probably going to run into trouble. Because in my experience, that confuses the custom Spark closure that's going on behind the scenes. Spark will try to create a closure when it's doing the map. It will try to create a closure with your global parser, and it runs into trouble. So declare your any variable that's referenced inside your functions, like map, should be declared locally rather than globally. Alright, gotcha. Trying to do a graceful shutdown. I mean, Spark streaming is great. You get your first Spark streaming going, and it's like, wahoo! But then, all of a sudden, you're like George Jetson. It's, how do I stop this crazy thing? Alright, well, there are issues at both the API and the application layer. If you looked at the source code behind Spark streaming in 0.9, and you looked at the source code for SSC stop, Spark streaming context stop, it just killed the threads. There was nothing graceful about it. Well, the situation has improved markedly in 1.0 and 1.01, but there are still some issues that are not resolved. If you happen to be using a raw TCP/IP socket receiver, as opposed to, for example, a Kafka receiver, that doesn't stop. And then this last issue, 2383, this is actually a startup issue, but I put it in here because it deals with the issue of Kafka offsets or high watermarks. And the whole reason you want to be able to shut down Kafka cleanly is so that it can commit back to Zookeeper your high watermarks. Well, there's an issue with high watermarks on startup currently in the current version. If you happen to have auto offset reset set to a value, then when you start it up, your high water marks get wiped out. There's also an issue at the application level. So here we have a DAG, a directed acyclic graph. And suppose we did a stop on our Kafka input D stream. Does that mean we can just immediately do our SSE stop right afterwards? Well, probably not, because there's data still flowing through our DAG. And if we have some like long running, by long running I mean a few seconds, processes, or we have bursty data, we may lose some of our data that's still flowing through our DAG. So one way to compensate for that is we could, if we could stick down a magic value through our pipes here. And then we stop our DAG only after we see our magic done ball, our green ball. I guess that's green. I don't know. I'm colorblind. And even though I made this slide, it was a couple weeks ago. We wait for that to come out the end. And when it comes out the end, then we set this global flag receive stop. And in our main, we just keep monitoring, waiting for this receive stop in a while loop to be set. Now, why does this work? Why can we set this global variable and have it work? Right? We don't have global variables in Spark. Well, it works because our for each gets run on the driver. So it's not really a global variable being communicated from the workers to the driver. It's already in the driver. So again, this goes back to Spark 101, differences between actions and transforms. This for each is an action. Related to Graceful Shutdown is being able to save and restore your state. So the key, perhaps the most important, in my opinion, API call in all of Spark streaming is update state by key. So this allows you to sort of count and accumulate things. So for example, if we're tied into a click stream, we could count the number of hits per web page coming out of our click stream. So in this case, the key would be the URL, and then the value would be this running count of how many times that web page has been hit. So the normal common update state by key function signature that we use is up here at the top. Spark streaming calls us once per microbatch, once per key. So per microbatch per key. So remember what a microbatch is. Spark streaming is not truly continuous. It breaks up the incoming stream into microbatches, for example, 10 seconds apiece. And in that 10-second microbatch, we have a bunch of URLs from our click stream. And so Spark streaming for each microbatch is going to call us once per key, and in that key we get a sequence of values. So specific. So if our key is, for example, the base URL, we might have a bunch of actual values that are that base URL plus our HTTP GET parameters, the question mark, ampersand parameters, and so we actually have different values to sum up. It's a sequence. It's all the hits to that URL within that microbatch within that 10 seconds. We also get passed to us the previous state, so the previous count, number of hits, and we're supposed to return back out of our function, the new state, the new number of counts. So if we were to shut down Spark streaming and bring back up our Spark streaming and start running this, all our previously set states are going to be set to 0. They're going to be wiped out, and all our counts are going to start over because this this state is sort of hidden within the internals of Spark Streaming. We don't actually have direct access to it. So the alternative, there's going to be a first-class way to do this in the future. I don't think it's targeted for 1.2, but there's the Jira ticket. It's a Spark 3660 where you can set your initial states. But you can actually do this anyway, even without Spark 3660 being done. There's another function signature available for update state by key. In your callback, I still call it a callback, sorry functional people, you receive 3 parameters instead of 2, and you output 2 values instead of 1 value. And what it is that you get to see all the keys at the same time, and then you return all the keys and all the states all at the same time. So on your first iteration, then, if you get an empty set of keys and states, or whatever flag, I mean, you can just populate that from what you've read off of disk before, and start with whatever states you had previously. Another gotcha is overrunning your batch duration. So if we're set to 10-second batches, and one of our batches takes 15 seconds of computation, we could run into trouble. And theoretically, you don't. Theoretically, it'll you can run over and then the next batch or two you can catch up. But we have received word from those knowledgeable with Spark internals that technically it's also undefined what happens if you overrun your batch duration. So the only solution then, and by the way, I have seen trouble. I have seen it work if you just overrun a batch or two, and I've also seen trouble if you overrun 10 batches in a row, for example, and get really far behind. So that means that you're really constrained here. The quote solution is to set your batch size for the worst case instead of the average case. That means that there's a batch size trade-off going on here, because in order to compensate for the worst case, especially if your streaming data is bursty, you may want to set your batch size to be, say, 2 minutes instead of 10 seconds, so that you can you have some elasticity there. You can handle the worst case. But 2 minutes means latency, right? So you have a trade-off between latency and the maximum throughput you can handle. Now here's a gotcha that really doesn't have a solution. So one of the big advantages that Storm has over Spark Streaming is that in Storm you get to acknowledge proper receipt and handling of the data upstream. So in Storm, if you run into an exception, an overflow condition, an error, or a delay, you can notify upstream on your DAG that you weren't able to handle that data, and upstream needs to resend that data to you sometime in the future. There's no way I know of to do that in Spark Streaming, unless you're using Flume. Just based on the comments in these Flume tickets, it seemed like somebody was aghast at the situation and solved the situation for Flume and Spark Streaming, but I don't think it applies to any other receiver such as Kafka. Another gotcha, and this is just dealing with Kafka, it has nothing to do with Spark itself. Kafka has, quote, at least once semantics, so this can lead to double counting. But the good news is that Kafka does not resend data arbitrarily. It seems to do it only if one of the nodes in the Kafka cluster goes down. So, normal situation, you don't need to worry about it. Another issue, another gotcha, is if you want to join two incoming data streams together, you really can't do that, especially if those two data streams have different parameters. Well, that's Spark Streaming. I'm next going to talk about GraphX, which is the part of Spark I know the next most about, and which I've actually worked with more recently. So the big problem with GraphX is that graphs are immutable. So, functional programming people love immutable data, which is great as long as the size of your data is not approaching the size of your memory. So if you're trying to work with a huge graph, immutable graphs are kind of a problem. But this is going to get solved in 1.2. And the solution is actually going to have a positive impact and flexibility for all of Spark, because they're going to introduce a mutable RDD. So the first use case that they're going to address here is GraphX, but it's really going to help everything, including SparkSQL. The other gotcha, kind of a surprise, is that there's no built-in API at this time to read an RDF file. So RDF is a standard file format for graphs. For example, you can go out there and download RDF files that are various consolidations of Wikipedia. And if you go to other graph processing systems, this is just something you expect that they provide. So the solution here is to wait for the Spark GraphX book that I'm going to be writing here. Starting writing now, and due to be out in the middle of 2015. Now, I'm not an intellectual property lawyer, but it seems to me that PageRank is patented. In fact, here's the list of patents from Wikipedia. So GraphX comes with a number of pre-canned algorithms: PageRank, triangle count, a handful of others. PageRank is particularly useful. It shows, the whole idea behind it is to see which nodes on your graph have the greatest reputation by being vouched for. But I'm pretty sure it's not legal to actually deploy the use of PageRank into production in a commercial for-profit environment. And I think it may even be illegal to even download this, which is an issue because GraphX is fully part and parcel of Spark. And so you download Spark, you're downloading patented code as far as I'm aware. I don't know if there's a license between Apache and Stanford. Stanford is the patent owner. But that's a question in my mind. Another issue is performance relative to other established graph tools. So these other established graph tools are usually written in C++, and that's where they get their performance boost. So this chart that I've pulled out of this paper is pretty typical of the charts in this paper, where Spark is running at or near the tail end in terms of performance. All right. So the next module I'm going to talk about is SparkSQL. So this image of the stack here is 3 months old, and I think at that time they were still trying to cling to the Shark name since it's so cool, even though it's a completely new module, SparkSQL. But it's just known as SparkSQL now. So the first gotcha you might run into is if you're just trying to reuse your good old Hive queries or Shark queries, because Shark was really just a shim to Hive. If you try to reuse your Hive queries on SparkSQL, you might run into some SQL incompatibilities. A lot of them are fixed in 1.2. There are some that are still open. So just be aware of that. Performance relative to Impala. This was a little brouhaha on the mailing list a week or two ago, where Impala, somebody did a benchmark and showed that Impala was twice as fast as SparkSQL. The response from from the Spark guys was, well, did you really do the performance tuning? And the people who did the benchmark were gracious enough to come on the mailing list and said, oh, yeah, we did, and we'd be happy to work with you to see if there's anything we missed. But that leads us to our next gotcha, or anti-pattern, which is assuming that you can, because this is Spark and Spark is fast, you can ignore performance tuning, and that's not the case. Just like with any other database, you need to do performance tuning. One of the nice advantages of Shark, so besides the obvious caching that Shark brought to the table, also brought this concept called data skipping, which I believe was invented by IBM. It's kind of a reverse index thing where, based on your query, it can completely discard what it calls data blocks altogether. So there's some pre-computation that happens where the data is broken up into blocks, and then metadata is stored for each block that indicates the range of values for the various columns within that block. So the query can just discard blocks without even having to scan or consider them. So Shark had this, and it's not currently in SparkSQL, though it's due to get into SparkSQL by 1.2. Next thing is I'm going to talk about is BlinkDB, which is a layer on top of Shark, and it's an approximate querying. So if you wanted to average the values of 1 million data records, BlinkDB can perform an approximation by sampling the data and only doing 100,000. The interesting thing about BlinkDB is it had this SQL syntax addition that allowed you to specify error bars, and BlinkDB would automatically figure out what the best sampling strategy would be and how many samples to sample. But this is right off of their webpage. Currently, BlinkDB requires Spark 0.9. So this also goes back to that first gotcha, which is BlinkDB is not part of Apache. It's an AmpLab project, so it doesn't necessarily get maintained along with the rest of the Spark stack. So just a couple of things about MLLib. MLLib is great, and it's growing, gaining more capabilities every day, every release. But initial versions lacked features for particular algorithms, and lacked entire algorithms altogether. But this is rapidly improving in terms of what's getting added into MLLib. And that's about it. I didn't really talk about Yarn and Mesos too much. I do know that if you go into Jira and look at Yarn, and you do a filter based on major critical on blocker not resolved yet, you end up with a couple of dozen issues. And that sort of echoes what I hear over the cubicle walls at Oracle about using Spark with Yarn. I mean, they have it working, but there were a number of issues. So that is it. And please follow my blog at datascienceassn.org or my Twitter handle at Michael Malak. Thank you.